think we can start.
Yep. Sorry for that. Can you guys hear me?
Yeah, we can hear you.
Sure. Okay. Good afternoon and good evening, guys. Today we would be discussing the practical part of the graph neural networks that we have been studying until now. Yeah. So this is kind of a what I felt here in this particular session, that it's kind of relatively kind of easier. I mean, except that we kind of, if we have a high level overview of how graph convolutional neural network works, and then I mean, effectively you can start using these concepts within the PyTorch framework. But then obviously, I mean, you have to start using. You also have to start including the deep graphical neural network library called DGL graph from that. So to begin with, here in this session, Alfredo, I mean, he kind of starts relating the graphs to self-attention. I mean, as we have seen before, where Professor X has has kind of related graphs to transformers, wherein the transformer itself, I mean, graph is transformer is a graph wherein every node is connected to every other. I mean, each node is connected to every other node. And here again, he also Alfredo, I mean, he says that that graphs are basically a kind of self-attention kind of network. So it kind of relates that to wherein there are a set of sequences, input sequences, uh, like in self-attention based networks, starting from xi, I being from 1 to t. Now here x could be would probably be an embedding sequence, a sequence, a vector of the embedding. It could probably be a node, or it could also be an edge. And again, this is not like it has a sequence as an order. It's just a set of uh, inputs. And then the hidden vector. I mean, the next output. I mean, the output of this, if you combine it with the convolution, would be the next. In a convolutional neural network, it would be probably the next layer of it, the output of the next layer. That would be the hidden vector h, and it's like a linear combination of the vectors within this this set that we are providing to the convolutional network. And then effectively, I mean, if it's a linear combination, then we can represent that as a matrix vector multiplication, wherein x is a matrix and a is contains the sequences itself of x. Yeah, so this is what he kind of briefly discusses over here, and then quickly, I mean, if you guys have done this week, I mean, this would be a little more easier to understand. And then after that, he goes into the notation of it, wherein Vj represents the jth node, and X is the input, and H is the hidden representation of it. Hidden representation, I mean, it kind of confused me initially a bit, but then hidden representation always the output of the linear combination of whatever matrix multiplication that you do with the input vector, or the input signal that we have. So V represents Vj represents the jth, or the jth node, or the jth vertex. And then after that, yeah, and this is about this. And then he kind of briefly talks about the adjacency vector A, wherein each element alpha j, which is of the adjacency vector, is set to 1 if there's a direct edge from Vj to V. And also the degree D is defined as the norm of this adjacency vector, that is the norm of the adjacency vector is the degree of this of this of the adjacency vector. And then later, I mean, as with any other neural network that we have seen, the hidden vector H is given by the following expression. I mean, so it's basically a linear combination using some sort of a vector V, vector X times A, that is the adjacency matrix. D is the degree of it, plus U times dx, and then you apply a nonlinear function to it, and then you get the output H. So I mean, the UX term takes into account the vertex V itself. So it's like a rotation, as we have seen before. So U times X is a simple rotation of the input. And
Quick question.
yes,
The D
yeah.
is just a scalar, right? It's a single number
Yes, this
in
is
the
what I've
equation
understood from
3.
here. Yes, D is just a single number. I mean, which comes from here, which is just a norm of the adjacency vector. Yes,
So each node will have its own degree, right?
each node will have its own degree. Exactly. Yes, perfect.
Okay.
Each
Yeah.
node
Thanks.
will have its own degree. Yes. Yeah. So this is what this is. I mean, like, so once we have this kind of an expression wherein you have a nonlinearity, you have some linear operations inside. I mean, this becomes very familiar to us, and then you can easily easily integrate this into the ecosystem of PyTorch, and then start doing gradient descent on this. So yeah, and then I mean, if you go into the explanation of Vx AD over here, uh, what we see here is that you are, I mean, like the self-attention that we have, the comparison that was done with the self-attention. This is what we have, that is X times A. That the columns X is scaled by the factors in X in the context of GCN. This means that if we have multiple incoming edges, that is multiple ones in adjacency X, so XA gets larger. On the other hand, if we have only one incoming edge, this value gets smaller. So I mean, he says that this is to kind of remedy the issue of disproportionate number of, or kind of have a proportionate number of have some sort of a proportion when the number of incoming edges are not same. So, and then again, this D is the degree which is used to divide it with this over here in this expression. So this is what kind of a basic kind of a graph convolution would be over here. But then later on, I mean, he starts to discuss about residual gated GCN. So this is kind of a special type of a graph convolutional network. So effectively, I mean, what's going on over here is that so this is like a special kind of a graph convolutional network, and there is some sort of a mathematical understanding of this. over here. And then after that, this particular, graph convolutional gated graph, residual gated graph convolutional network is being applied to a problem for graph classification. I mean, what type of graph classification we can have. So to kind of really kick off what graph classification is, I was thinking of to kind of quickly go through the library which is being used in this class over here. So there is this library called deep graphical DGL, deep graph library. So it's a Python package for easy implementation of graph neural network, and it's kind of built upon PyTorch and all of the standard frameworks that we are used to. So this is kind of a little kind of a tricky when I started reading this, but the tutorials are really good. There is one tutorial here, I mean, which I felt that this particular tutorial is being implemented or tested here by Alfredo, but then he applied it and used it for the residual gated GCN. I mean, he applied the same tutorial for graph classification, but then he applied it for this particular kind of graph convolutional network. So let me kind of quickly look into this code that we have over here. So what's happening over here is the problem of graph classification is that you have a certain type of graphs. I mean, like here, for example, because this is an artificially created data set over here, where you have a cycle graph, a star graph, a wheel graph, different types of graphs, and then the data which we have is kind of a set of all of these graphs, and we use the graphical convolutional neural network to classify what kind of a graph we have in the end. So here, I mean, if you see here, a simple graph is being created, a simple data set, because now we have to kind of create data set out of thin air. So this is an artificially created artificial data set that we have over here. And so this is a function which is a class which can be used to create a data set. So now this data set is, if you look at what mini this would be, so sorry, let me search for it here. Yeah, so here this is a way of generating graphs, mini GC data set. So wherein you can define the number of graphs that you want. So that is the number of data points, or I mean, corresponding to images, it would be the number of images over here. And then the minimum number of vertices that we want to have within the graph, and the maximum number of vertices that we want to have in the graph. So we're kind of creating artificially this data set. So it's 80 graphs that we want. Of the minimum size would be of 10, and the maximum would be of 20. So and then these are simple here, because this is a data set, you obviously have a graph and then its corresponding label, and then you can simply plot it over here and then see what kind of a graph is this. So this is a kind of a graph, class 0 kind of a graph, which kind of corresponds to this cycle graph. So I mean, this is what he's kind of doing over here in this session. So to kind of come back to the theory of the residual gated GCN. Now here in this what he says is that the residual gated GCN has a few mathematical expressions, a few expressions on how the embedding or how the hidden layer is calculated. So I mean, why is it called gated in the sense that residual in the sense that because we are taking into consideration the signal itself, and the reason why it's called gated is that because the node features edges are also being utilized with the node features. So here, as with the standard GCN, the vertex V consists of two vectors, the two vectors being the input X that we have and its hidden representation, that is after the transformation, the representation that we have H. But then because of this being a gated GCN, the edges also have a feature representation. I mean, the edges also have a feature representation, and then those edges are utilized when you utilized for the linear transformation for calculating the hidden representation. So where EXJ represents the input edge representation, EHJ represents the hidden edge representation. I mean, so even the edges, the input edge would be EX, and its transformed output would be EHJ. That is the after the transformation that we get is EHJ. So effectively, what we are doing is you have to take into consideration the input edge vector, the input hidden representation as well of the edge, and then effectively you do a multiplication with the input node vector, and uh, then you find out the hidden representation of it. So that's why it's called residual gated GCN. So now in this feature is now X is the node vector, and B is the linear transformation which is applied to it, and EJ is the edge feature. So basically, EJ also has a different way of calculation that we can go using equation 7 over here, and then this also takes there is a little bit of nonlinearity also applied to the edge representation over here as well. So what you're doing effectively is kind of taking into consideration the edge representation and also the node representation, and then calculating the next or the hidden representation of it. So the way EJ is calculated is by multiplying C, D, and E, and these C, D, and E are also linear transformations that have to be learned during the gradient descent. I mean, all of these all of these matrices, that is A, B, C, D, and E, are the matrices which would be learned during the back propagation.
So difference between, sorry.
Sure.
No, I was thinking that difference between GCN and this one. With GCN, it's inside the summation. There is you are taking all the neighbors features and weighting it by adjacency and the inverse of the degree, right? Whereas here, you are doing the same thing, but instead of using A and D inverse, you're using this, the nonlinearity against the edge features and then convolving it with the.
Exactly. Yes. Yep. Okay.
I have a question.
Sure.
What is the difference between in equation 7? Like, what is the difference between EJ and EJX, the EXJ that you see? I mean, along with C. EJ and EXJ.
And yeah, so EJ is actually calculated using EXJ. So using equation 7, if you see here. So EJ is calculated using EXJ. So EXJ is actually known to us, XJ is known to us, and X is also known to us. So EJ
So
is kind of, yes.
EXJ represents the edge between X and any vertex J, right?
Yes, X and the, yeah. So EJ would be
I mean,
this particular, this EJ would be this, the node that you have, that you are at, and between that node and the jth node or the
E is
jth
the
vertex.
edge.
Yeah,
E
is
is
the
the
edge. Yes,
edge. Yeah.
is the edge.
yeah.
Yes.
So what is EXJ then?
The edge that starts or incident on X, maybe.
Yeah, the edge that is connecting the node J and X. So the
Not
representation is like this. I mean, what he absolutely considers this particular, for example, this is X, for example, right? If this is X and this is the jth node, right? This is XJ, this is X, and this is XJ. So the edge which is connecting XJ and X is EJ. Sorry, EXJ. The embedding of this particular edge is EXJ. Uh, does that make sense?
Yeah, but that EJ is the same thing, right?
No, EJ is calculated using this. I mean, if you look at this equation 7 over here,
So
so
EJ is
EJ
like a
is
new representation of
exactly. It's a new
EXJ.
representation of the EXJ. Yes, it's a new representation of that. Yes.
Okay.
And
Yeah.
the hidden of it, I mean, that this EJ is utilized over here in this equation, and then you get the hidden representation of the edge, of the jth edge that like we have seen over here. And this is again utilized to calculate this particular expression over here. Okay.
Yeah.
And then again, all of this is substituted back into this particular expression, and then you have the hidden representation of the nodes of the vertex that is uh, that is this particular node. The expression of this, the hidden representation of this particular node. Okay. So I mean, I didn't get the intuition of this. I mean, the paper is pretty complex. It requires a little bit more reading multiple times. I mean, this is something like, what I felt like when I was looking at this. This is something like an RNN, wherein we have multiple sequences which are kind of substituted into each expression, and then you kind of effectively get another expression at the end. Okay, so yeah, so this is effectively a kind of how a mathematical expression of how a residual gated GCN would kind of calculate the convolution, the graph convolution of of nodes. Okay, so yes, so yeah, so coming back to the code now. So let me see if I can. Okay, so as we have seen here, I mean, in this in the tutorial that we have seen, so the task that is being done over here is graph classification. So the problem is graph classification, and these are the basic imports. Because DGL is a separate library, it has to be installed using the standard pip install function. So yeah, so here, I mean, so to kind of do this task, we kind of start creating an artificial data set. So this is, let me just restart this notebook. So the way you can create an artificial data set is using this particular class, mini GCD GC data set, wherein you can you can define the number of data set and also give out minimum number of nodes that are there in the graphs that are required. So just to kind of see how the graphs are. So here we generate 8 graphs, and all of these graphs would probably have a minimum of 10 nodes and a maximum of 20 nodes. So I mean, so again, you can set this, you can fix this by seeding it to, if you want to have some sort of repeatability, you can set the random variable here itself, so the seed to a particular constant. So these are the type of graphs which are generated now. So class 0 would be a cycle graph, and class 1 would be a star graph, and all of these different types of graphs. So this is how the data set is generated using that. But here we want to add some signal to the domain. I mean, here what we are doing is, apart from having the data set that we are generating, we want to add some features to it. So here, this is just a plain graph without any features or without any embedding. So this function generates just the graphs without any values or without any embedding, which is being assigned to either the node or the edges. So here, this function create artificial features. It takes in the input as a data set, and you can start assigning features to the nodes and the edges. So each graph in the data set, you can assign all the nodes a certain feature and all the edges a certain type of feature. So here, for this problem, what is being done is that that each node is being assigned with the degrees of it, with the degree of the node itself. So each node would have an embedding that would be the degree or the number of edges which are incident on it. And for the edges, it would be the number of, I mean, each of the edge would be the feature vector for the edge would be the size. I mean, it would just be a simple vector, and the size of the vector would be equal to the number of edges that are there in the whole graph. Yeah, so this is how you populate and create the features within the data set. So effectively, I mean, a graph is created and and then we have access to all of these nodes data and the edges data over here. So yeah, so to create this artificial data set for our application here for this example, so this is the training set, which is of 350 graphs, and the test set is created of 100 graphs, and you apply these features to it. So now you have the training set with the featured the features that we want over here, and also the test set. So if you just kind of analyze this a little bit, I can quickly print train set 0. So this is the first data point. Sorry, so I have to run this as well. Yep. So here, if you see here, this gives a description of what the graph is, what the first value is. That this is a graph which has 50 nodes, and then the number of edges is 45. The node data, meaning the features of the node, is of the shapes of of size 1, and the edge has also a size of 1. So here, if you see here, uh, obviously, I mean, because the embedding here that we are assuming for each node would be the number of the number of edges that are incident on it, or the degree of that particular node. So obviously that would be a single number. So that's why the shape over here is this. And similarly for this particular for the embedding for the embedding for the edge embedding as well. So the shape is 1 over here. So this is how the data set of that we are trying to classify using gated GCNs looks like. Okay, so these are the equations that we would be implementing in this layer. I mean, just to create a gated GCNA. So this is the way we do the convolution in this in a residual gated GCN. So all these have to be implemented here. So yeah, so here, I mean, there is this new terminology which I came across. I mean, these are called message functions. I think this is something related to message passing. If someone can jump in and quickly, explain what message passing would be, because that would be kind of very useful if we kind of start doing all of this implementation below. Someone, yeah, go ahead.
So message passing is basically what we learned in GCN as well, right? So you take a node and each neighbor or each node emits its own features, right? So there are two phases, as you can see here, right? There is the broadcast phase, I think it's called, define, accessing. Okay, the reduce function and the other function, right? The message
function, yes.
Okay.
Yeah.
So in the message function, each node broadcasts its own features to all its neighbors, right? And this happens on all nodes in the graph, right? And in the reduce stage, each node, aggregates all the features that its neighbors gave it. Right? So you can think of it in MapReduce terms in Hadoop, right? The first phase, the message, is like when everybody is sending out something, right? So that's the map phase. And in the reduce phase, you're taking all the inputs that are coming in from your neighbors and aggregating it to form some neighbor features. So you could do some, max, mean, whatever, right? Pooling, some kind of pooling operation.
Yeah. Okay. Got it. Yeah.
So, yeah.
Yes. So yeah. So if we kind of go down here and start defining the gated GCN layer, so you are initializing, all of these matrices A, B, C, D, E. And we are also initializing the batch normalization. Here, so we have these five matrices which are initialized, and all of these A, B, C would be utilized over here, and these would be learned during the backpropagation. So here again we have the message function. So this is again an implementation of this mathematical of this expression over here that we have. So yeah, so here if you see here, bxj would be edges.src bx, which comes from here, and ej is this, that is edges data. I mean, effectively what we're doing here is we are utilizing the embedding of each node and the edges, and then combining it or doing a linear transformation and then summing it over here, and then finding the transformed embedding of the edges. So this is what is being done over here, and then and then we are assigning this, and we are storing the effective or the new transformed edge embedding ej into this data structure over here, and then returning it as well. That is the bxjs, because this is also This is also needed because we need bxj and ej as part of this particular calculation. And similarly in the reduce function as well, wherein we are kind of utilizing all the embeddings which are kind of incident on this particular node. Yeah, so here, so if you notice here, the first line is we are simple assignment of it. So we use ax, bxj, and ej from the nodes, and we utilize that and then convert that into sigma j. That is this particular sigmoid, and then this expression over here, that is eta of ej, is calculated in this particular form over here, and this is utilized and then effectively calculated as the hidden representation of it. Yeah, and then that is returned over here because this is the broadcast, if I'm correct, Sujit, right? This is the broadcast of the broadcast step.
No, I think of this as the aggregate step. So the message function is the broadcast, right?
Messages, okay.
Yeah, and you can see it here, right? So in the bxj, it says nodes.mailbox. So essentially, like, everybody is mailing him their features, right? And then he picks it up from the mailbox and then aggregates it, right? Yeah. So,
okay. Yeah. So in the forward pass, we have this graph. For each graph, we do all of these calculations, and then we access these pre-calculated values of x, a, b, t, and e, ex, and also the embedding, the edge embedding as well. And then because of this particular, because each node has to be updated because of this broadcast operation, and this function updates all the nodes and all the edges with these calculations that are being done. Okay. And yeah, and then again, now H becomes the result of a graph convolution, H and E.
I think update all basically does one cycle of message and reduce, right? Internally. So it does every node basically broadcasts, and every node will then aggregate, and this is encapsulated in this update all. And after that, what is the stage after that? So that's where you get out of H, you'll get the value of H and E and so on, and we can move forward with that.
Okay, and then this normalization happens, I guess. So the normalization of the graph node and the edge node size. Yeah, and then there is a step of batch normalization as well, and then you have the standard nonlinear activation, wherein you apply reload to it. And then because this being a residual graph convolution network, so you also add the signal itself directly to it.
That is the AX here somewhere. Yeah.
Sorry,
that is
this one, right?
X plus H. Yeah.
X plus H. Yeah. And similarly, also for the edge as well. So there is a residual connection even for the embedding as well. So that becomes E underscore X plus E. So the forward pass is this. And obviously the backward pass would be the gradients of all of these calculations that we are doing over here. Okay, so this is how a graph convolutional layer is defined. So I mean, if you do a comparison here of what the tutorial mentions here is, sorry, is it this? Yeah. So this is a simple classifier, and there are inbuilt graph convolution layers as well within this library. I mean, you can directly import it from here. So you can directly call the graph convolution layers as con1, con2, and then you can simply implement it here. So this is basically a new kind of a graph convolution using the residual gated functionality. So there are some inbuilt graph convolution layers as well within this particular library. Okay, so this is what I wanted to show here briefly. Yeah, so here again, this is a simple multi-layer perceptron, a simple network that you can define over here. Then we can come up with the final network that we want to have. So first we have first the linear layer, which forms the embedding for which is for the this is the input of it, the first layer, and then the second layer for the edges, and then the previously defined gated GCN is created over here, and we also use this previously created MLP layer, and yeah, and then here we have the input nodes which are given to the embedding layer over here, and then we also have it which gives us the output as H, and similarly for the edges as well. And here, using the gated GCN, we apply, I mean, depending upon the number of layers that were defined, the number of depths that we want to have, that is based on this particular value of L. So we apply the graph convolution to it repeatedly, and then accordingly we get the hidden representation for the nodes, and also the hidden representation for the edges as well. Yes. And then here, this is the classifier. I mean, the final layer is taken, and then the mean is found out, and then the mean of all the nodes that we have, and on top of that we have an MLP layer which does the classification for us, and then this is returned as the output. Okay.
What is the hidden dimension here? It's what does it represent?
The hidden dimension, I mean, so this would be the dimension of so the input has a certain, the input dimension is dependent on the number of nodes that we have, and the hidden dimension would be the number of hidden representations that we want to have. This is something like the neural network, I mean, wherein we define the input and the output of a linear layer, right? So
is it the node embedding dimension?
Pretty much, yeah. It's basically like, if you take NLP kind of things, where your input is basically like a sparse vector, and you go through an embedding into a smaller, lower dimensional dense vector.
Yes.
Okay. The idea is exactly the same here. So your
I was
node
confused
sorry,
because I was confused because I thought we started with a single number that represents each edge and each node, and not an embedding.
Yes. So okay. So in the GCN, whatever the GCN is, right? That layer will take it can take larger dimensions. So in this case, it's like a toy example. I think it's just one, right? Your vector size, the input vector size is just one. But you could think of having multiple sizes as well, and then you can from one you can make it like it will actually increase in dimension here, right? So
yeah, so there's an increase in dimension. So if you notice here, the dimensions have been increased to 100.
Yeah, so it becomes 1 to 100.
Exactly. And then so and then the output dimension, because this is an eight-way classification because we have 8 types of graphs, so the output dimension would be 8, and the number of layers of graphs that we have is 2. So it's kind of a repeated application of the same graph twice.
And that corresponds to basically 2 hops, right? So you are essentially pulling for each node you're pulling
Yes.
the features of its neighbors and its neighbors because of this two-layer thing.
Two-layer. Okay. Yes. Yes. Correct. And sorry, let me go. Yep. And then the network is instantiated over here. If you see here, the first layer that we have, which has an input feature of size 1, and then the output is 100. Okay, but then when the gated GCN starts, the input features are 100 and the output features are 100 here. So yeah, so we have the gated GCN layer who are starting from here to here, and then the other one starting from here to here.
I think you pointed this out last lesson that the size of the when it passes through the GCN, any kind.
Yes.
Yesterday or last week it was just a GCN, but the size never changed, right? So
the size never changes. Yes. Yeah. So yeah. So here again, because this is an MLP layer at the end, we can we can convert this layer from, because we need to have an output of 8 because of the 8 classes of graphs we have, and then the last layer is of size the output is of size 8. Okay.
I think there is. Can you go up a little bit on this, on the definition of the thing? One more. Here. Okay, yeah. So this is gated GCN. There is this DGL.mean nodes, right? So and if you notice, the output of the GCN is like features 100, and it's also got edge features, I think, right? It's 100 by 100. Whereas this one, it basically flattens. So this is kind of a mean pooling, but it's a specialized mean pooling from what I understand. So even in PyGeometric, they have these. So I'm actually learning PyGeometric in the other class, so that's how. So they have 3 kinds of pooling, like mean, max, and sum, right? But none of these are like global max pooling that we have in CNNs, right? These are different. Okay. So for some reason, they have these specialized functions even there. So I just wanted to point that out. And this is
so let's look into it quickly. I mean, let's see what it says.
I think you got it here.
Yeah. So DGL.mean nodes, the averages all the values of a node field, features in graph, optionally multiplies the field by a scalar. Okay, whatever weight we have over here. Okay, so we define a graph here. We have 2 nodes and mean nodes PG. Okay, so here. Okay. This is graph 1 and graph 2. DG1.mean nodes of PG. So okay, 1, 2, 3, 6, and 1, 2, 3, 2. Okay. So effectively, when we say mean nodes, it would kind of calculate the mean of all the nodes, right? Or is it mean between the 2 layers?
1 times 3 plus 3. Okay. It's doing something different here.
G2 is DGL graph 3, and G2 this is okay. So G2 is
it's a weighted graph. Mean. It's a weighted mean. Look, so it's 1 times 3, right, and 2 times something.
Okay, this is mean node. But to define a weighted mean, a weight has to be assigned. So there is no weight which is being assigned over here. And you see here, it says graph. And so basically it averages all the values of node field, that is the features in the graph. So if you want to have a weighted mean, this would
you have to put it in. Yeah. Okay.
Put a weight over here, and then I'm not sure if this is weighted mean, the weight field. If no, okay, yeah, sure, yeah. This is the weighted mean, and yeah. So we have these 2 graphs, G1 and G2. The node attributes are this, and mean nodes would be PG. So effectively, the features which are listed as H, which are listed on the H, the mean of that is calculated. So for example, here the features of H are 1 and 2, and the features of H in graph 2 is 1, 2, and 3. So that would be the mean of these two, 1 plus 2 by 2, though. So that's 1 plus 2 by 2 over 2, and 1 plus 2 plus 3 over 3. Okay, so yeah, got it. Okay, so it's effectively the mean of the nodes.
Yeah, here I think we could have reused, we could have just used global mean pooling 1D or something instead.
Okay.
Got the same results.
No, but then we have to be specific, I guess, only for the hidden representation that we have, because the data that is stored within the data data structure is in the form of a dictionary.
Right.
So by specifying this H, so it kind of picks up that H from that, and then it finds out the node the mean nodes of this hidden representation H.
Right. But we could have just taken these two lines and replaced it with y equals global max pooling 1DH, right?
1DH, okay. In the regular, got it.
Yeah, I think this is more for correctness, so for next time when we do it in real world, we should use these kind of things. Yeah.
Okay. Yep, and then this is given to the MLP layer, and then that gives us the output as a 8x1 vector. Okay. Yeah, and then these are some helper functions. This is for accuracy. This is pretty much the similar what we are used to, the first two lines over here. This is the data loader, which creates the data loader for loading into the training, wherein we can define the batch size, whether we want to shuffle it or not, and also collating it. And then and then we also input the train set over here, and we define this the iterator function over here for the graphs and their labels, and also the S-norm and the S-norm of the node, and also the S-norm of the edges. Okay, so if we just run this, so here we just check out the sizes of this, the batch of the graphs, because this is a batch size of 10. Let me just put some sort of okay. Yeah, so this batch graph, the number of nodes is 125, the number of edges are 583, and again the size of the feature vector for the node is of 1, and also the edge is also 1. And the labels that we have over here is, because this is a batch size 10, so we have these labels. This is graph of type 1, type 5, 4, 7, 7, 2, 6, 5. So all these numbers correspond to the class of the graph. So these numbers 3, 4, 5, 6, and 7. Okay. Yeah, so yeah, here I'm kind of just wondering, why would we have a different size for the, because the edge size is different, because the number of edges are different.
Right.
Yeah, so because the number of edges are different, and different graphs have different number of edges, that's why we have 583. And for X, that is the signal that we have, it depends on the number of nodes that we have for each graph. And it's like you have 125 nodes overall. So out of 10 graphs, so in total we have 125 nodes. And for these 10 graphs, in total we have 583 edges. I mean, this is a really kind of a counterintuitive way of representing these, these size of the nodes. Because I mean, here it kind of gives, does not kind of clearly mention that whether is it the number of nodes per graph or the number of edges per graph, or is it the total number of nodes or total number of edges, right? Am I?
Yeah, I would have expected 10, but then again, since everything is linked,
Yes.
maybe, that's why you're carrying the entire vector, the node feature vector and the edge feature vector together.
Yeah. By looking at batch graphs, I cannot say how many, what is the batch size of the graph that I have of the data set that we have created.
Yeah.
By looking at batch labels, I can tell that. But
you
then
can do len batch graphs and see what you get.
Let's see.
Yeah.
Len batch graphs is 125.
It's still 125. Yeah.
Still 125.
It's almost like it doesn't respect the batch size.
Mm-hmm. Can we print out and see what this is? Okay, so we cannot do this. Okay, so this is not a list.
It's probably an iterator. You have to list.
Yeah, it's an iterator. Yeah, exactly. Yeah, it's an iterator.
So you can do next on that, and
next. Yeah. So print next batch graphs. It's not an iterator. Okay, probably I could do this. Nope.
Actually, maybe no. I don't know if it makes. I don't know. Batching makes sense even in case of. Although.
Why wouldn't batching make sense? Because
no, here you're doing complete graphs. So each row should be like one graph.
Each row is a graph and its corresponding label. Yes, this is
right.
Yeah.
And your embeddings are, the node embedding is 125. And no, wait. So num nodes are 125.
The number of nodes, yes, and the number of edges are 583.
I think it's like maybe a connectivity matrix. I don't know. I mean, yeah.
Sure.
It does make sense. You're right, but it doesn't seem to reflect anything here.
Sure. Okay, so this is about that. Yeah. Yeah. So this is just a test of it, just the forward pass, whether it functions, whether it.
Wait, and here we see. You see here. You see it's 10. So it is finding batch labels, right?
Yeah, it's finding over here. Yeah, true. No, but then this is batch labels. I mean, here, if you notice, batch labels is correct.
You're printing batch scores, so you got 10 of them. So, but when you do a forward pass with batch graphs, which is of size, X size is 125 and Y size, E size is this, you actually get 10 scores. So it is doing 10 at a time.
It is doing 10 at a time. Yes, that's correct.
So maybe, there is some other, metric that we are missing here that will give us 10 out of this guy.
Probably, yes. Probably, yes. So batch scores what size is 10.8, yes. Okay. And then, because this is a multi-class classification, we use across entropy laws. Pretty standard steps over here: optimizer, zero grad, backward, and optimizer step. So even the backward pass works fine. and then the training function. There is nothing special over here which I have noticed. The standard training steps that we have been used to. Okay, then this is the evaluation step and the training step over here. So now basically I'm running this on the CPU itself. I mean, this is without the GPU.
While it's running, can you take a look at the data loader on the docs for the data loader?
This one?
No, on your left-hand panel.
Okay,
right?
fine.
Yeah, look at the docs for the data loader. So where we saw the batch X, batch Y stuff, right? And see how to get to the batch. Just curious. Is it it's a DGL data loader or a PyTorch data loader?
This is a PyTorch data loader. This one is PyTorch.
Okay.
I think this is PyTorch. Let's see. Yeah, this is PyTorch data loader.
Okay, cool.
Okay. Okay, so data loader is this. Batch size. This gets complicated. Let's search Google. Okay.
I think basically if you iterate on that and look at the length of the thing that was iterated or that came through, that would be.
That would, you mean by going through?
This one is done too.
Yeah,
I was just trying to fill up some time there.
Sure.
So, basically, why the 10 was not coming. It's
exactly.
batch X,
You
batch Y is
answered.
probably, batch X and batch E are probably not the right things to look at. We are looking at something different.
Something different. Sure.
Yeah.
Okay. So so this is pretty much trained for in 39 epochs. We got an accuracy of a training accuracy of 0.99 and a test accuracy of 0.99 and training accuracy of 9829. So effectively, what we're doing is we are kind of using a GCN to do a classification of graphs. So I mean, like classification of images. Images being classified into different classes. So we are kind of classifying the graphs into different classes. Okay, yeah, so this is it for this one, for the practicum. If you guys have anything to add. Okay, let's see. Yep.
I just had a quick comment on the earlier statement that you made, the number of features not changing after each graph convolution, right? After each GCN layer. So this is exactly what happens in attention as well. After, if you have an attention layer followed by another attention layer, the number of the dimension of the embedding does not change. And what happens is essentially same thing in attention and in a GCN. You are just doing some kind of averaging of the representation. I mean, you're doing some kind of averaging to get the new representation. Yeah, so there is some commonality there, that the dimension does not change as you go through each layer. Yeah,
good point.
Yeah. So I mean, so like how Sujesh mentioned just now, I mean, when we have two layers over here, so it's effectively like a two hop situation. I mean, so it's effectively we are taking into consideration kind of two nodes away from the central node that we have that is in consideration, right?
It's yeah, exactly. It's very similar to attention, right? That as Gautam also pointed out, right? So
yeah,
essentially you are attending on, in the first layer, you're attending for each node, all with all its neighbors, right? And then in the second layer, you're taking this globed piece and attending all its neighbors with this, right? So now you have, so it's like a two layer. You're pulling. I think of it as pooling as well. I mean, you can basically think of it as taking all your neighbors and creating like a super object, right, in the first layer, and then creating all their neighbors and creating another super object.
Yep.
So,
yeah.
Yeah, the only difference is attention. All words are neighbors. I mean,
yes.
everyone is a neighbor of each other.
Exactly. Yes. Yeah. I mean, so that would here in this particular case, I guess it wouldn't kind of, as Professor X had mentioned, that it wouldn't kind of be useful in the sense that because there aren't any because all the nodes are connected to each other, there wouldn't be any information which is coming out of it.
I wonder if you could create more, nicer. So we know that n squared, the attention is n squared, right? And but attention is n squared, where for large n for large documents. But if we could do it in a graded way, like this, right? So you say, okay, all my neighbors are in the sentence, right? So you do your first layer of attention with that, and you create a sentence attention vector, right? And then you say that for each sentence, all my neighbors are my sentences in the same paragraph, right? And you create a vector out of that, and then you say all my neighbors are my paragraphs in the document, right? So maybe in 3 layers, that might be less, order of computation wise, that might be less less of a problem.
Has that been tried out anywhere?
I don't know. I mean, I don't think I've heard this. So maybe we should do this. Yeah.
Yeah, I mean, yeah, I mean, if for attention, I mean, we could, like how you mentioned, if it is a graded way of combining, I mean, can we do it randomly and then see how things would figure out? I mean, do some sort of a random connection or have a way of randomly generating edges between nodes and then see how it pans out. I mean, instead of having a fully connected, I mean, fully connected in the sense wherein all nodes are connected to each other.
Right. Yeah.
Sure. Or that could be some sort of a rule-based kind of a connection between the attention itself can be rule-based, not like it is connected to each other. Yeah, so that's a possibility. I mean, I don't know. That needs to be checked out. Okay. Yeah, so this has kind of a so Sujit, I mean, so apart from DGL, I think there is pi geometry, you're saying?
Pi geometric, yes.
Okay.
But according to assessments, DGL is further ahead than pi geometric in a lot of features, and it's also cross-platform. So just like here we put a PyTorch backend, I believe you can also do a Keras backend, but I'm not sure. You can do an MXNet backend for sure.
Yes,
but I'm not sure. I'm not sure about Keras.
Okay. Okay. Yeah. So here, I mean, there are various tutorials for message passing, graph classification, and then working with other heterogeneous graphs as well. Yeah. So this is this theme pretty accessible and pretty easy to understand. I mean, this particular library, I guess. Yeah. Okay. So anything else to add?
Okay. If we don't have any more questions, Tayyab, thanks for doing the session. Do we have any questions or comments from anyone else? Okay. So next week we have structured prediction on energy-based models. I think we don't have a volunteer as of now. So if anyone's interested, let me know. I'll post it in the channel as well. Yeah. Okay. Thanks, Tayyab. Thanks everyone else for joining.
Also one more thing. For the hugging face guys, can we meet right after? We may be able to use the same channel as well, I mean, so that we don't have to go out.
Yeah. I think that's I think we don't need to end this meeting, right? I'll just
Right, exactly.
continue. Yeah, but it'll be recorded. That's
Okay. Okay, let's end the meeting then. That's fine.
okay.
I'll just create another one.
Okay.
Cool.
Okay. Thank you. Thank you, guys.
Thank you, guys. All right. Thanks. Thanks,
Bye-bye.
Dad.
Thank you. Bye bye.